Okay, let's just pretend this isn't the third time. So today we're gonna talk about image processing in the browser with an X. And before we get too far ahead, I'm gonna introduce myself. I'm Paulo Valente. I'm Brazilian. I'm an electronics and computer engineer. I've worked with Elixir for the past 7 years, and for this talk, I think the most important part is that I am part of the NX core team. And in this talk, we're going to discuss a bit of the prerequisites that we need to understand image processing. So we're going to go over what are matrices, and then what is an X, how computers represent matrices, and then we're going to discuss a few important operations that we need for image processing. And then we're going to go into a live demonstration. Plus a small surprise that I've also recorded. So matrices, you can think about matrices as a collection of numbers. You have a number, and then if you group numbers into a list, you can call that list a vector. Vectors aren't necessarily just lists of numbers, but for the purposes of this talk, I think we can just think about them as that. And then matrices are just the two-dimensional extension of that. So it's just rows and columns, and numbers are organized into that table-like structure. And NX is the numerical computing library for Elixir. It's what enables Elixir to do numerical computation in a competitive manner to Python. It is inspired by NumPy, JAX, and all of the Python ecosystem. And the most important part is that NX brings tensors, which is a multidimensional extension of matrices that we just discussed. And also it allows deploying code to the CPU, GPU, and some other specific types of hardware and runtimes. And then NX is the base layer. In the previous talk, we saw Axon. Axon is built on top of NX. So everything that we're going to discuss about NX also applies to Axon to some extent. And now we have one of the simplest examples we can see for NX. So we have a module, and at the top of the module, we're importing an NXDefn. And by importing an NXDefn, we gain access to the defn macro. And the defn macro works mostly like a normal Elixir function, but it's gonna have some overrides, and most importantly, it's gonna be able to group all of the computation that's defined inside it into what we call an NXDefn expression. We're not gonna get too much into what an NXDefn expression is, but just know that that is one of what enables NX to do what it does. I just realized my camera is off, so I'm gonna turn that on again. So here we have some example function calls, and notice that we can call it with numbers, tensors, some combination of those. And as I said, NX will group the computations in a nested NXDefn expression struct. And then when we call the function, it's gonna compile the code into the defn expression, and then it's gonna be executed or compiled before executing through configurable compilers. And then different compilers will be able to target different backends. Sorry, will be able to target different devices. And the compilation of an X code happens at Elixir runtime. It's what we call a just-in-time compilation. And through NX, ERI, EXLA, EMLX, we're able to access different devices. So we can deploy to CUDA GPUs, to the Metal GPU on Macs. We can deploy to the iOS GPU via NX ERI, And we can also deploy to the browser using NX through WebAssembly. And before we see NX applied, let's take a step back into how computers represent images. And generally, we use RGB images, or in some cases, we see RGBA. And that's basically one matrix representing the red color, another matrix representing the green color, another one for blue color. And when we have a fourth channel that's called the alpha channel, that's for transparency. That's how you get PNGs that can have transparent backgrounds, for instance. But we just need to worry about the fact that it's just a collection of numbers. So each color, we can call that a channel. So in this case, the image has height, width, and 4 channels. And then each pixel, it's gonna be like the pixel on row 4, column 5, that's gonna have 4 channels. That's one way of thinking about it. And then there are other formats that have fewer channels. So grayscale will have either just one channel if it's just a black and white image, or maybe 2 channels if you want to have the alpha channel for transparency. There's a lot of flexibility on how to do these representations. But generally, images are a matrix or a collection of matrices where each position represents the intensity of the color or the channel that you're representing. And then for image processing, there is this mathematical operation that I'm going to first describe and then we're going to see in action, which is the convolution. And the convolution applies a small matrix that we call the kernel to each part of the matrix, and then it slides over the kernel over the input matrix. And that yields a new matrix that's kind of like a weighted sum or a local weighted sum of the input matrix. And that's used for a lot of things. It can be used for edge detection in classical image processing, and that doesn't use neural networks. It can be used for blur, sharpen, which is kind of the opposite of blurring. And these last two are what we're going to use today. So here is a small animation of the convolution at work. And we just get the kernel, slide it over the input, and we just put the result on the output matrix. This is a very simplified representation of what a convolution is, but this is what we need to visualize when using it. And then if we have the convolution, we have this subset of image processing, which we call kernel filters. And then the kernel filters are just special kernels that we can define that we know apply a specific operation to the matrix. So the uniform blur, we can notice quite quickly, it's just the kernel is just a matrix that has all positions equal to each other. And this weird number is just because we always want the kernel to add up to 1, because it's kind of like an average. So the 0.0204 is just because this matrix is 7 by 7. And then if you do 1 over 49 in this case, you get 0.0204. The Gaussian blur is another type of blurring that's more flexible. And in this case, we have, you can kind of see it symmetrical over the center just by looking at it. You don't have to worry too much about how this function is defined. You just have to imagine that it's like if you have a small mountain that's really smooth and centered at the middle of the matrix. And then if you add up the matrix, add up all of the positions, you'll also get 1. And the Gaussian blur has more parameters than just the size. It also has a sigma that will tell us how flat or how high that mountain is. So it will concentrate or make it more diffuse. And then sharpen, it's a bit harder to visualize, but it's just you get a matrix that has 1 at the center, that's the delta, and then you get 2 times that matrix minus a blur kernel. In this case, I'm using the same kernel as the Gaussian blur. So you see, for instance, the second row, second column is 0.0209. It's the same value there, just negative. And the sharpen can be thought of as if it were the opposite of a blur, like the inverse operation. Not quite that, but it gives us the basic idea. And then let's go to a live demo where we'll be able to better visualize these things. So I'm gonna stop my camera on Discord and allow the browser to access it. And now we have at the left the input image and on the right the output image. And when I select a filter, I can see as NX compiles new code for the filter, I get a notification at the top right. So I got a new update there, and we can see that as I increase sigma, as I increase kernel size, the output image gets more blurred. If I go to the uniform blur, we'll see that it behaves a bit differently. So it needs a larger kernel size to get the same level of blurring as a Gaussian blur. If I go back to kernel size and really increase sigma, we'll see that it's quite a bit, or at least a bit more blurry than the uniform blur. And sharpen, we can now see that it gives more of a crispiness to the image. It's the best way I can describe it. If we go back and forth between the Gaussian blur and sharpen with the Gaussian blur kernel, we can really compare how one is kind of the opposite of the other. And I've also added a tint filter here, which is just a way of colorizing the image. And then for the tint filter, you'll notice that it doesn't keep recompiling, because as these are just weights and the shape of the image and there is not really a kernel at play here, we can just use the same NX function for each one. In the case of the other kernel filters, we need to recompile basically one NX function per kernel size. And then we can really colorize our image here, or just slightly by changing the alpha channel of the tint filter. And going back to our presentation now, I've also recorded basically the same code. It's not quite the same because I didn't support tint, but this is running on device on my iPad. This is just a screen recording of my iPad, and I'm interacting with it in real time as well. And the nice thing is that this code is actually running on device. The only data that travels between the server and the device is the compiled bytecode because NX is compiling things on the server, but there are no images traveling out of the device. It's just happening on the iPad with LiveView Native. And this is the small surprise that I had separated for you. Um, so we've seen how matrices and kernels interact to produce image processing. We've seen NX in action, especially NX being deployed to the client. And by deploying to the client, we avoid consuming too much bandwidth. After it's a lot cheaper to just send the bytecode in terms of bandwidth, to send the bytecode and then to, instead of sending the bytecode, sending images over and over, especially if you're gonna process basically every frame. And yeah, there are quite a few interesting applications that can arise from this capability. I've shown image processing, but you can do basically anything that you can with an X on the edge. And the code is available on my GitHub at this repository. I'll share this on the chat as well for people that are watching live. And yeah, thank you. You can reach out to me on X and GitHub, LinkedIn as well, same handle, and Blue Sky, it's Valente.social.
Nice, Paulo Valente. Thank you for your presentation.
Mm-hmm.
Uh, amazing, amazing.
Does anyone have questions?
I have a question. I can use an X to compress image.
Yes, there is. Since we're in the browser, let me go to Scholar. Actually, um,
Because in my project, the feature is streaming video, but
mhm.
not works with full quality videos. I think about compress
Right. So there are a
stream.
few ways of going about this. If you just want to compress to reduce bandwidth, you probably just want to resize the image and then do the downsize it and then upsize it on the other end. And for that, I would say eVision is the way to go. eVision is the the library that binds OpenCV. I'm not sure if I can. Yeah. So eVision is just OpenCV bound to Elixir, and it also has an NX interface. So you can interoperate eVision with, let's say, classical NX. And if you just look for how to do things with OpenCV, it's quite easy to translate the Python OpenCV code to what would be the eVision code. There are a few conventions that you learn quite quickly when trying to do these types of translations. And then
Nice.
yeah, I would recommend eVision.
I research about these things. Can we use NX in computer science as well, leveraging the Erlang cluster to distribute heavy computations?
So not quite yet. Um, if we go to the Elixir NX repository, you're gonna see that recently I merged this pull request, which is an XDefn graph, and this allows us to take an XDefn expression and using some split rule, we can split that function into stages. And the stages are basically just what we intuitively can think about. So if I split on the dot computation, it's basically gonna take and turn all of the arguments to the next dot function into arguments to a new function and just create a divide into the graph there. And this is one part of the puzzle. The other, which is currently just as a proof of concept in this pull request, is that we can then take a graph and allocate it throughout an Erlang cluster. So if you go to this open pull request, the final test here, it actually shows us taking an XDFN expression, creating a graph of an XDFN expressions, and then running that graph across two Erlang nodes.
Nice.
And this is soon going to become a library that's more generic than just for NX. But then we can use it to, let's say, coordinate distributing load between two GPUs on the same machine, or distributing NX computations over different machines, or even if we get too crazy about it, we can um, run part of the NX code on the client as well. So what I just showed with WebAssembly or deploying to the iPad, but connecting that with a larger computation that happens throughout a Beam cluster. And I'm also working on deploying an X with Halo AI acceleration to nerves. So that also brings nerves into play here. And for people who don't know, nerves is how we can run the Beam on embedded devices such as the Raspberry Pi.
All right, thank you. Have some question? Anyone? Anyone else? Question for Paulo Valente. Where do you live in Brazil, Paulo Valente?
I live in Rio.
Rio.
Yeah, Copacabana actually. So Lady Gaga is just over there.
uh, someone will write in a question for you on the moment.
Yeah.
You can read it or only sharing?
Oh, I have the Discord window open right now, so I can see the people are typing as well.
Gaga likes Elixir too. Oh my god. João writing the Bible? Stop typing now. The viability of using Raspberry Pi with Erlang Elixir is something I really like.
Yeah, I'm giving a joint talk with a friend of mine, Vittoria, in Codebeam Stockholm on June 2nd, I think. It's early June, so basically in a month. And we're at the final stages of getting things to work such that you can use like eVision, EXLA to run regular NX code on the CPU, but separately you'll also be able to call um, into full-on models with the Halo AI hat. Um, the Halo AI hat is basically an accelerator that can run. Let's call them closed models, as in you can run um, YOLO for object detection, but you can't really deploy arbitrary computations to the device. So the way I see this happening is that we'll have a subset of things that run on the hat, and then you can use NX to communicate data in your pipeline and then have those models at the core of your pipeline. But you can also think about, let's say, taking a Raspberry Pi 0W, such as this chip here, which is a lot less powerful than a Raspberry Pi 5. And then you can use like similar devices to that, cluster them to a Raspberry Pi 5 that's running on site, and then use that as your, let's call it your on-site data center for for computations.
Nice.
So
I think
yeah.
about make a big cluster with network
Hmm.
with the many GPUs. This works today.
Yeah, maybe by the end of next week we'll have something. Let's see. But um, as soon as we have distributed graph execution working, we'll be able to have rules like um, basically each node declaring how much memory it can hold. And then I can say things like, hey, this neural network takes up 100 gigabytes of VRAM, and I have not 100, but let's say 30 gigabytes. And then I have an RTX 4090 beside me that has 24 gigs. That computer back there has an RTX 2060 with 6 gigs. But you also have to have space for the competition itself. So let's also put this Mac into the mix as well, which has 32 gigabytes of shared memory. And by like summing up all of this, you'll see quite quickly that we do have in this room more than 30 gigabytes of VRAM available. And then if you split your computation in a smart way, you can allocate as much as you can on the 4090 and then the 2060 and then the Mac, and have all of them interconnect with the distributed graph executor that I'm working on. And then,
Nice.
yeah, you'll be able to
Have,
leverage your home cluster.
have a new question from João.
Mm-hmm.
Can you share the patch for anyone who wants to contribute to the NX project? What do you think they need to know first?
It really depends on what you want to contribute with. We recently have been working on better documentation. So you'll see that there recently has been merged a cheat sheet pull request on NX Core, and then I have an open pull request for a cheat sheet on Axon, and then we also revamped the introductory documentation for NX. So I would start by validating that we didn't miss anything there, and then in doing that you'll be able to um, see if you missed anything, really, if we missed anything, and then also learn and act in the process. And I think that for NX core it's a bit harder to add things because I wouldn't say it's feature complete, but let's say it's 95% there in terms of what the core library needs. And then the missing 5% are basically too hard for beginner contributors to really tackle as a first contribution. So I'd say start by going through the documentation, submitting pull requests or issues for things that you think are not really um, clear, And then I'd say that the ancillary libraries, so Axon, Scholar, eVision, those might be able to, or EMLX as well. Those might accept or have room for um, more meaningful feature contributions. Oh, and for NX Core itself, more guides are basically always welcome. You can open an issue if you have an idea, and we can discuss there, or you can just ping me on the Elixir Slack or Erlang Ecosystem Foundation Slack. I'm always there, or actually on the Discord here as well.
Other question for you.
Mm-hmm.
This is a very nimble question, but could it be possible to combine GPU and CPU combinations based on having a cluster of raspberries or
Mm-hmm.
Pi-Is, which AI hat and without AI hats?
Um, um, as it is today already, you can just cluster the all of the Raspberry Pis that you have running nerves, and then it's just as simple as you knowing which ones have the hat, and then uh, let's assume that we've released the NX Halo library. We'll be able to just run the model on one machine and then on one of the Pis, and then send data over through Erlang RPC between the Pis. If people haven't um, really experimented with this, Erlang RPC is um, sorry, got distracted. I think we want this. Um, so Erlang RPC makes it really easy to do distributed calls over a cluster, a Beam cluster. I think we're basically on time right now, so uh, and my voice is wanting to go away as well, so I think we should stop here. And if anyone has um, any questions afterwards, you can reach out to me and we can talk about those.
Nice. This is good talk. I I have many ideas with your explanation. Explains. I
Nice.
reuse all talks today. Uh, Now is my turn to present.
Thank you.
Nice. Thank you too.